Hi there, Turgeon here, bringing you physics from afar. We learned about electric charges. We learned that they affect other things. And if you think about it, the electric charges affect only other electric charges. Opposites attract, like charges repel. That's called Coulomb's law. We actually looked at the equation to compute those forces. Well, now we're still talking about forces, but we're interested in a different question. How do those forces or how do those charges kind of create a space around them that would affect other things? That means electric fields and that means magnetic fields. Here we have an electric field, you can tell because it's a charge, not a magnet, just a simple positive charge. What I'm going to do is I'm going to look at what if we were to place an object at different points within this electric field. So the object is kind of away from the charge right now. It's really simple. Let's look at the force. If I were to bring this charge closer, we know that there's more force on it. You can tell because you know about Coulomb's law, but what's not so obvious is you can also tell because the lines get closer together. These are called electric field lines. When those get closer together, that means that the force is greater. So if I bring this object, which would have to have a charge, it could be positive or negative. I'm really just kind of trying to mark the location there. But if I bring this object close, the lines are generally close together. When I bring it farther away, notice the lines are getting more spaced out. So that has less force on it. Also, if I bring it close, it took more work, took more energy to get it there. So that object also has more energy if it's in a more dense region of electric field lines. That may be obvious when the charge looks something like that, but what if we make this a little more complicated? Now I'm going to show you an arrangement of two charges. Now we have another electric field diagram. This is what's great about electric fields is they can handle more complex situations and they can map out the space around it to show you what would happen. Now if I bring the charge out here, I know that it's got a relatively weak force and pretty low energy because the lines are pretty far apart. They're also pretty far apart here. If I bring the object, again, this is a charge and it could be positive or negative. If I bring it here, you can see the lines are a lot more dense. So this would be a really high density region with a lot of force on that charge and a lot of energy on that charge. Now, if it's a positive charge, the forces are actually going to go along the field lines. And if it's a negative charge, they'll go opposite to that. So it kind of also sums up the direction for you. Like right here, we know it's going to get most of its force from this charge, and it's going to get some force pulling it off to the right as well. So this is mostly down, but also to the right. So that's charges with their forces and energies. But what about magnetic fields? Magnetic fields is not about charges anymore. It's about a compass. So here we have a magnet that is creating a magnetic field. And yes, this happens to be the Earth. We know that the magnetic field that would be experienced way out here in space is weaker because the field lines are pretty spread apart. And it turns out they're actually strongest near the poles. That's why you get these effects of the northern lights. Those are caused by the magnetic fields. Now, one of the things you're going to notice is that we're talking about I've separated into like magnets and charges. So I'm saying where the field is stronger, that's where another magnet would be affected, which means like a compass. A compass really is just another little magnet that's got really low friction and it's in space and it's being affected by this other magnet, in this case, the Earth. But if you bring a compass near a household magnet, or especially like one of those really strong neodymium magnets, it's going to really respond to that. It's going to show a lot of action and it's going to show a lot of movement. Now, there is an exception to this rule of magnets are affecting other magnets and charges are affecting other charges. If the charges happen to be moving really fast, or I'm just going to say moving at all, if the charges are moving at all, they are affected by magnetic fields in complex ways, which are too detailed to go into in this video. But if you look at the northern lights, it's because the sun is emitting these charged particles at very high velocity and they spiral around. And when they spiral, they emit energy in the form of light. So to summarize, the answer to this question is, how do we show the effects in space? We draw magnetic field lines, we draw electric field lines, which show the strength of the force and they show the strength of the energy of a charge or a magnet in space. This has been Physics from Afar.